go ahead and get started. We're happy today to have Sean Lorenz. Sean Lorenz was the Director of Internet of Things Strategy for LogMeIn. He's currently moving on to start his own project. He has to decide after. He's very active in the Boston startup community, and he's passionate about Internet of Things and computational neuroscience. He's going to be talking about deep learning in an Internet of Things environment. Please welcome Sean.
Thanks everybody for sticking around. I know everybody's mentioned it's a beautiful day and we're blocking that view so you can focus. Because I know we all want to get out there. So it won't take a lot of time, but I want to give you just kind of a big picture view of deep learning and how it can be applied to the Internet of Things. So really I just want to quickly say what I'm going to talk about, which is deep learning, where it is today, then move on to kind of the IoT, since this is deep learning plus IoT, so we'll see what the state of the industry is for both. And then I want to talk about a very particular flavor of deep learning called recurrent neural networks, and I'll talk about why. And then lastly, I want to talk about building an actual recurrent neural network in Python. So for this, I was going to actually do a demo, but I'm not going to be able to because I actually just purchased. Where is it? Has anybody heard of Estimate? It's a really cool company. Where is it? Sorry, I'm digging through things as we talk. I have it. It's a special. Here it is. So I wanted this to come in the mail a couple of months ago, but it just came in this week. So I was going to go through an Estimo sticker and hearables, and I'll talk about what this is. But I didn't have time to code it up, so my apologies. But I will at least point you to some really good GitHub repositories for how to do this. And I will also probably do a live demo of this in the next month or so. So if you're interested, let me know and we can chat. So where is deep learning today? Anybody who's been following deep learning knows that it's hot. It's super hot. You know, that's what all the kids are talking about, right? Google's acquiring pretty much every deep learning data scientist that exists. You know, they're gobbling up everybody. So there's a lot of activity from a lot of the big players, Microsoft being one, Amazon, Google, all the big kind of players in the market really see the advantage of this because they have massive amounts of data and they want to analyze it and start predicting on it. And I think Google sees themselves as almost like an AI company. If you look at a lot of their products, really what they do really well is deep learning. And did anybody go to the Deep Learning Summit here a couple months ago in Boston? I highly recommend it. It's by Rework. They have a whole Deep Learning Summit. It was amazing. Some of the biggest companies and some smaller startups were sharing their results. And I really recommend, if you're interested in deep learning, go and checking out the Deep Learning Summit. So, kitties and puppies. Google does a great job of analyzing static images. It's in fact, when I was at the Deep Learning Summit, they were sharing some results of categorizing food, where they could tell they were trying to determine how many calories were in each dish. And it blew up in the Twitter sphere, if you will, as much as a deep learning tweet can. You know, and a lot of people were talking about how interesting this would be for anybody who's interested in monitoring health, as far as diabetes, and really understanding health in terms of food. So a lot of the problems with you're using some of those food counters, those calorie counters, you have to enter everything manually. If you can just take a picture of it, it makes it really easy to start doing some prediction and really monitoring your health and say, hey, don't eat this instead in real time. So deep learning has done a great job for analyzing static images. It's also done a really good job for analyzing text. You'll see, of course, again, Google, using it to analyze your search results. The reason when you start typing even 1 to 2 letters, it gives you a really actually accurate, fair prediction, is because they're using deep learning to predict, not just using n-grams, which is a popular technique with natural language processing, but far more robust kind of correlations between letters, words, and sentences. There's some really nice, if anybody's interested in that, there's a really cool program called Word2Vec. which is extremely cool. Richard Socher is actually has a new company called MetaMind, which is doing some really interesting stuff in this space with text. But when it comes to the Internet of Things, the smart home and all this sort of new kind of sensor-based data, it gives a bit of critics. And the reason for that is there's something about the static nature of the first two that lends itself really well to traditional deep learning. Whereas the kind of time series sensor-based kind of data that you're getting off the IoT, it requires something a little different, which is why, have you seen anybody talking about deep learning in the Internet of Things yet? Maybe one or two people. There's actually a great guy in London who started to do this. There's a new class in Oxford University that they're starting to teach this, which is awesome. You can take it online. Problem is, deep learning is really something from the blast from the mid-'80s. So, anybody who's old enough to know who this is George Michael. So, bad 80s pop, or good if you like George Michael. But the problem was, deep learning has been around, only we called it back then, back propagation. So, we gave it a new and a sexier name and did a few tricks, and now we have deep learning. However, like I said, it's been around for a long time. This is an old paper on odor sensing. And really, back propagation back in the mid-1980s was used on sensor data pretty extensively in the machine industrial space. So back before there was the Internet of Things and deep learning, which are kind of the new language around both of those terms, back around 25 years ago, 30 years ago, oh my gosh, 30 years ago, there was a whole lot of work being done in the industrial space for analyzing sensors, and that was called the machine-to-machine or M2M space. So this has been analyzed a lot using artificial neural networks in this space for decades. But now we're trying to apply this to a whole new, larger data set, and that's why the intersection of deep learning in kind of what Jeffrey hinted, who is one of the forefathers, the godfathers of deep learning, has done a lot of new, interesting things to take back propagation and make it much more amenable and adaptable. Because there were a lot of issues with back prop back in the 80s. So the Internet of Things. This is where we are today. I've been working on this space now for several years, and I just got back from Dreamforce in San Francisco, so I'm a little tired. Which is, anybody who's been to Salesforce's Dreamforce, it's 140,000 people running everywhere, and it's insane. But they just announced their big IoT cloud, and so what it shows you is that the business side of things are really starting to finally catch up. The IoT is kind of at the very top, if anybody follows the Gartner hype cycle. The Internet of Things is very at the top of the cycle, of the hype cycle. And everybody's trying to move in this space as fast as humanly possible. All the major Fortune 500 companies, if you are a manufacturer or someone in the data space, you have an IoT strategy. Everybody's talking about it. No one knows where it's going, so they're just trying to iterate as quickly as humanly possible. But really, what the problem is we talk a lot about connecting all this stuff, but no one's really talking about what we do with all this data. We have a lot of these large companies. LogMeIn has provided a really great IoT platform called Xively, which has done a great job of helping. If you're a connected product manufacturer, let's say you're Lutron, which they sell connected dimmer switches and lights and blinds, and you want to connect it to the internet with this phone. So right now, I can mess with my wife and turn the lights on and off in Marblehead, right? So she doesn't like it, but all that data, really where it's been in the IoT has been just getting it connected, because really that's been really hard. There's been a lot of massive issues around security, around connectivity. Some of the leading edge just connectivity platforms took 4 to 5 to 6 seconds at sometimes. When I hit the light on, wait, light goes on, okay, great. If it's slower than you flipping the switch on going across the room, then it's not okay. You want something that has a high speed, a high reliability, and we are just now getting to that space in the IoT industry. So now let's assume that that's all solved. What's next? What do we do with all this data? And that's really what I want to talk about here is, how you analyze all this massive amount of time series-based data. So there's a lot of different industries that I think we can apply deep learning and IoT. The automobile industry, there's a lot you can do. Of course, there's heads-up displays that analyze your vision. Are you staying awake? Also, context-aware applications. So there's actually a company called Automatic, which hooks into the ODM port. And so what it'll do is it'll understand how you're using the car, if you're braking, all these sort of things, and it'll send you can actually access the API and start getting all this data in real time. You say, oh, you're braking too hard, or you're driving, you're swerving too much, or all these sort of kind of statistics you can start analyzing. And of course, there's the self-driving cars, which are a whole other industry, which you could also see as part of the IoT. There's personal applications where you can start to figure out, okay, I'm wearing wearables, fitness, all this sort of stuff that you wear on your body, and also integrating with other data sources. So the IoT, I think what's interesting is it's not just merging sensor data, but it's going to mix with the existing daily kind of information that you consume on the internet already. So you can imagine where you might have like a daily need, where it's understanding all the information about your body, but also how you consume Facebook, Twitter, and all these other sort of data sources in your life, and start finding and predicting around everything you do in your everyday life, which I think is extremely exciting. I think there's going to be a lot of cool stuff that happens with startups in this space. Obviously, the smart home. I heard plenty about that, so I'm skipping it. Marketing, there's a lot of this data. If you're a company creating an IoT product, internal kind of statistics are going to be used where you can collect all that data and start finding ways to better market, hyper-targeted marketing to these individuals, or also just to say, okay, do I know enough about who my target market is? How can I better figure out how to give something back to them? Insurance, one issue with one big actually industry that's really getting into the IoT is the insurance industry, based on context-based. How do you use your car? It could be home insurance. There's going to be price breaks if you're using certain kind of devices and energy plays. The smart city, again, you have the mixture of smart energy policies. There might be sensors on every stop sign and all the different kind of places as you interact with the city to better flow traffic. There's a lot of different interesting ways. Big Belly is actually one company that has been providing those smart trash compactors, garbage cans. But really what they're starting to do now is even more interesting, is they're using these smart cans as hubs. So they're becoming basically like mesh networks, where you can now hook all these together and start putting other sensors on it to understand how people flow in the city and how we can better manage that. And I know they're going to be talking more about that soon. Predictive maintenance. This is an interesting one. If products break, if let's say your Dyson, vacuum cleaner breaks, or it realizes that your hose is about to go. There might be sensors on your connected vacuum that'll say, tells your app, okay, we did some deep learning on how the product is being used, and we predict that in 2 days, your hose is going to break. So we're going to automatically have that data through an API, send it to Salesforce, send it to your ERP system, deliver the part to you, and schedule a technician to come out and fix it for you within the time that happens. So that's really what's going to start happening with predictive maintenance for consumer products as well as for other B2B and industrial contexts. Building automation. We waste so much energy when, have you ever driven through the city and just see tons of lights on in different areas of commercial buildings? It drives me nuts. It's such a waste, and I think there's going to be a lot we can start doing. Or you go to a building and the water faucet's still running and you have to turn it off for somebody. Those sort of things will be started to automate for people who run these buildings to better understand, when does a light go out, and how can you automatically figure out how to automate that process for lighting or energy or heating and cooling. Supply chain is another interesting one to kind of optimize supply chain. Anybody who's interested in the traveling salesman problem, it's kind of fun. And then last is healthcare, and I actually think healthcare is the biggest possible one that I'm actually personally interested in. I think there's going to be an enormous way that we can take, for example, the home. I think the smart home begins with the smart health itself, where we'll be able to understand in your everyday world, if someone has one of your loved ones has Alzheimer's, you'll have all these different Bluetooth enabled and wearables, everything in the home, so you can analyze that to see if there's any deviation from the norm to say, hey, I predict that there's something wrong, you need to call grandma, you need to call a caregiver. So these are a bunch of different examples, and I want to just focus in now on a particular health one. I have two kids, they're 6 and 4, but when they were first born over at Beth Israel, my daughter came 16 weeks early. So she was born at 24 weeks gestation, which is extremely early. So one thing I noticed, when I was doing my PhD over at Boston University, is I was actually writing an algorithm for real-time EEG processing for locked-in syndrome patients, where I was taking EEG data and predicting where they were looking on a screen. And I was sitting in my daughter's NICU room and noticed suddenly she would just stop breathing. And all the alarms would go on and the nurses would be yelling and cursing, bring my daughter back to life. And it was really dramatic. And I started wondering, what if you could actually take all this data and actually predict with it? What if you could actually figure out, using deep learning or some sort of time series-based architecture, that how to predict, even 10 seconds ahead of time when an event was going to happen. So I think what's going to happen in the future is we're going to have all this in the home too. There's going to be a time where we have all kinds of medical devices, whether it's wearables or pulse oximeters or kids that come home with GI tubes, where we can take all these different data points, pulse oximeters, cardiac monitors, and even the smart caps with how much medical dosage. We'll be able to take those and then learn from each of those, then combine them to find higher levels of learning. And this is what deep learning does best, is it takes in different vectors, different sources of information, and then it learns on those. And then what it can do is it learns higher levels, more abstract views of that data. So in this case, you might want to have a pulse oximeter, and at the top you have frequency bands. So these frequency bands, this is where, this is, if anybody who's done kind of signal processing, you're like, wait, why would you do deep learning this? And I think there's arguments for both. We can talk about those if you're into that. So what it can do is it can learn frequency bands. It can learn then, different predictions on the oxygen space within those pulse oximeters. And then you might be able to combine that with the other sources, so it'll learn now a higher level. Say, okay, if you combine the pulse oximeter and the cardiac monitor, can we determine if that patient is in a certain state? Like, are they happy? Are they sad? Or maybe not sad. Are they well? Are they not well? Let's just stick with 2. And then you can do even higher levels. And then what you can do from there is, if you're in the home, because a lot of these kids or adults go home, what if you could actually send that directly to your nurse, a visiting nurse, or directly pop that into any HR so that the doctor can call you up and say, we think something's not right, you should come in. Reduces hospital readmission rates. There's a lot of different interesting things now you can do because we're predicting on that data in the home. So this is what the Internet of Things really is good for, is really helping us in our everyday world do different kinds of sensing about what's happening. And that deep learning allows us to now predict on that and predict the future. So now there's a very particular type of deep learning I want to talk about, and that's called recurrent neural networks. And why? It's because it's good with time. So time series is what recurrent neural networks do best. And why recurrent neural networks? Mainly because they use feedback connections to change the weights. So in a typical deep learning, that propagation-based algorithm, it's purely feed forward. There's nothing that goes back, other than the error signal, and that's different. But the actual connections don't go backwards, so I'll make that. And it also retains a memory over time. So what it's doing is when you have an input, it looks at the past time steps and tries to learn on that as well. So that's what makes it interesting. So with those combined, you can learn much more complex temporal patterns. So this is, I mentioned my little Estimo stickers, which I was bummed I didn't get to code up. But what's interesting here is you have these little stickers, and in each of these stickers, it's really cool. They have a temperature sensor, an accelerometer, and a BLE sensing device. So they're using Bluetooth Low Energy to transmit all that data on a little sticker. So you could put 10 of these. I was going to put them around my house just to see, what my wife and kids are opening most or doing. Just it could be the temperature between the upstairs and downstairs in our house. There's a lot of ways you could have fun with it. But what an RNN does is you observe. So you basically get a bunch of time series data, and you learn from that, make a model. So this is our little RNN model at the bottom left, and then you can generate some data from that. And then you feed that data back up to the real physical world. So you get a closed feedback loop system. So over here on the left, we have the more traditional feed-forward back propagation algorithm. See, you'll notice everything's just moving forward. Keep marching forward. Whereas recurrent neural networks look really like a mess sometimes. But what's interesting about it is you can often, if you're familiar with artificial neural networks, they kind of feed back onto themselves. So it updates the weights, and there's a lot of reasons why people say you can do that, but I'm not going to get that far into the weeds with this. So because the previous vector of activities is used to compute the vector of activities in each time step, recurrent neural nets are able to retain a sort of like memory of previous events in order to make decisions. So just quickly how the RNN works is it uses something called unrolling. So what that means is it unrolls over time. So instead of just having one node at each time point, what it does is it says, okay, at the top here it hits the first input. It says, okay, I'm going to learn on that for the network. Good job. But what I'm also going to do is I'm going to do t minus 1, t minus 2, t minus 3, the exact same thing. And then it's summing what happens on the weights over all those time periods. So it's learning over time, and it understands context, basically, of how things are moving through that time to develop a much more complicated memory in the system. So, a little math. Just quickly, I'm just going to go through this. Basically, a traditional kind of neural network says, hey, you get an output, which is y, and the basic principle of most statistics and neural networks are you multiply a signal times a weight. So you have this matrix of weights, and then you have an input, which, in this case, accelerometers, moving. And I want to say, okay, is it moving in the refrigerator, or is it moving on my closet upstairs? There might be different patterns for those, who knows? So that's the traditional way of things. But now, with recurrent neural nets, what it's doing is we have a sequence of inputs, which is xi, so those are the different inputs. But then we have corresponding the output, which is calculated here by having a weight multiplied for all those other outputs like I mentioned. So now you can incorporate the past into one equation from a traditional kind of backprop net. So, this is just a little more detail, which is just showing now we can expand that. That was just one input. Now you can expand that into an input layer, a hidden layer, and then the output layer. So all this just to say is it takes an input here, and then that sigma here is a transfer function, so it's like a sigmoid. And what it'll do is it'll calculate an output to say which class things, and then it says, oh, you picked the wrong class. We think it's in this one, not this one. So send the error back through. So what this is doing is it's still doing backprop, but in a different way. So I realize I'm almost out of time. But what's interesting is it's more biologically accurate because of that feedback. It unrolls through time. And now you can determine the optimal weights through this rolling. And it's basically deep backprop over time. So I'm not going to go through this, but if you want the slides, I think we'll have them available. So I use Python's Theano library. I highly recommend using Theano. It's really hurts my head. Actually, the first time I tried to learn it, it's using tensor math. to basically figure out how to optimize matrices and vectors for processing. But it's extremely efficient, and everybody's starting to use it. I recommend there's a really good deep learning tutorial on Piano, so I would check those out. So there's a light version, which is like one simple code. I don't have it here. Or you can use, there's a heavier version, and you can look up those. And I also have a bunch of resources here to help you out. Oh, went through that way too fast. I think that's it. Thank you. Let me know if you have any questions. Questions? Yes. Did I look at what? DQ? Deep Q. No, I've heard of Q learning, but not deep Q. Okay. Yeah, there's a lot. The industry is changing so quickly. I mean, every week I feel like there's a new kind of technique that's coming out. I'd actually really like Q learning has worked really well in the past, but it has kind of suffered from catastrophic forgetting. So what's really bad about that is, you can learn a network and then it'll predict really well on that. But if you have a continual stream of new stuff coming in, it blows up all your weights. That's bad. So especially in the IT where you want it to be continual learning, I think the future is going more towards something like not even RNNs, but even into active learning, which is a kind of a hot new term. But it uses a lot of the techniques of Q learning, deep learning, and now active learning is trying to figure its way through the floor. So look up active learning. Yeah?
Still mean how much of algorithms are going to be deployed in embedded environment, how much has to be run online?
That's a great question. So before I was at LogMeIn, I had a startup called Neurala. We were doing brains for bots, where we were building navigation systems for the Mars rover. And one thing that we had a really hard time with is how much of the visual system do we process locally versus how much you do in the cloud. And I think there's a lot of interesting, if you haven't heard of it, it's called fog computing. So fog computing is trying to determine the optimal balance between processing on the edge and processing in the cloud. I really think for the IoT, what we're going to do is we're going to have a lot of pre-processing. It's vision, figuring out edge vectors, and really doing something on the edge, on the actual device. But a lot of these IoT devices don't have good processing power. So what you're probably going to do is process it on the gateway. So there's going to be home gateways, if you're in the home, for example, that can take a little more beating, where you can process even more. So there might be light processing on the edge, a little more processing on the gateway, and then you send the rest to the cloud and send it back. So my guess is it's going to be distributed, and I think there's a lot to be done in figuring out how to optimally disperse those computations. Yeah. Anyone else? Thank you.